Okay, next up on this lovely history day is Dave Patterson, who's the Pardee Professor of Computer Science at UC Berkeley. He's won the von Neumann Medal and the Eckert-Mauchly Award. Famous, of course, for RISC and RAID, and now a master of revolutionary work and great acronyms at the same time. He was also on my thesis committee. He's going to be talking about the past and future of hardware architectures. Please welcome Dave Patterson.
Okay, I found out on Wednesday I was giving a talk here. I'm talking about the past and the future. They said I could talk about any operating system topic I want, so I'm going to talk about hardware. So the half of the talk will be about the past, 50 years of computer architecture in 12 minutes, and then we're going to talk about some exciting things happening in the hardware and architecture in the future. So it's already been referred to a few times, but 50 years ago, IBM had this big problem. They had 4 different lines of computers with 4 different instruction sets, 4 different markets, 4 different business teams. So IBM bet the company that they could unite all of those markets and machines besides one instruction set. The IBM 360 was announced on the same day with many different models of the same machine. And this thing is still, with minor modifications, running today. Those of us from that era, when we see the, and this is where the for those of you who wondered, where did the 8-bit byte come? It came right, that's where it came from. Those of us from that era, tears come in our eyes when we see one of these green cards. This is the summary of the instruction set. You'd either keep it in your shirt pocket or your purse, but that was the whole instruction set. Well, when IBM was going to do this, in designing computers, even today, the 2 parts of it are kind of the Datapath, the brawn that does the work, and the control, the brain that tells it what to do. The hard part's the brain, the control. So Maurice Wilkes, the author of the EDSAC, he came up with this idea that we could make control design a lot like programming. And in his era, the logic was a lot more expensive than memory, and read-only memory was a lot faster and cheaper than random access memory. So IBM bet the company, and they used that idea. So those different models there had different, the models on this slide had a difference in data path width between 8 bits and 64 bits, and kind of the clock cycle was different, so almost by a factor of 4. And then what's shown on the slide is what they charged per year to lease it, and then what that be in today's dollars. So to lease the high-end machine for 1 year was $3 million, right, for 1 year. So IBM bet the company, and they won. IBM was a very, very profitable company. What happened is Moore's Law continued. Everything got built out of the same thing, out of MOS transistors. And RAM and ROM were the same speed. Memories could get bigger with Moore's Law, so that allowed more complicated instruction sets in the microcode. And the classic example of this was the VAX instruction set architecture in the late 70s. So the microprocessor guys weren't that good at computer architecture, so what they would just do is look at what the big guys did and imitate them. So the mini computer, the mainframes. So the most ambitious project of that era, which has already been mentioned today, was the Intel 432. Gordon Moore of Moore's Law at Intel recognized that at that time they had an 8-bit computer, the 8080. The next instruction set that Intel did would last forever. They'd be stuck with it forever. So he hired a bunch of PhDs, sent them up to Portland, Oregon, and said, invent the next great instruction set. And they did a capability-based architecture, lots of microcode. Alas, it took them too long. They were going to be years late. And so they told Gordon Moore that they weren't going to hit the target. So he did an emergency project that in 10 weeks designed the next instruction set. And then they had like about 3 or 4 months to build it. So they actually did, in an emergency effort, hit the target that Gordon Moore needed. And because they hit their target, IBM, who was coming up with the personal computer, needed a 16-bit microprocessor. The Motorola 68000, which they preferred because it was like the 360, was late, so they picked the 88. They thought they'd sell maybe 250,000 of them, and they sold hundreds of millions, which solidified the x86 as the dominant instruction set architecture, and Gordon Moore was right, and it's still with us today. So people started looking at the microcoded machine. This is a picture of John Cox standing next to the IBM 801, which was the first RISC computer. It was a It's a mini computer, but VLIW, so big, expensive computer. And he did this interesting experiment, he and the people there. He said, let's just use the simple register, and load store instructions from the 360, ignore all the rest of them, and see what happens. Well, what happens when they did that, it ran 3 times faster. So, and a couple of guys from DEC studied the VAX architecture internally. They found that 20% of the instructions were responsible of 60% of the microcode, and they were almost never used. And then I actually took a sabbatical also at DEC because my research was in microcode tools. And I came away with something that complicated is going to have bugs. And so I came back from Berkeley after sabbatical, wrote a paper, said if we're going to imitate those kind of instruction sets, there's going to be bugs, and so we should build repairable microprocessors. That paper was rejected, and because they said that's a stupid way to build microprocessors. So in my mind, I had, well, if it's that complicated, it's going to have bugs, and it's a stupid way to build microprocessors, so that led me to the RISC work. So the transition from, if you think of that microcode background, from CISC to RISC there, it's instead of using the RAM memory to have microcode, instead we're going to put simple instructions in there, and then the content would change depending what program you're running. And by the way, if you made instructions simple, we could pipeline them so they'd be a lot more efficient. And also, by the way, the compilers couldn't use those complicated instructions anyways. And as Moore's law continued, we were able to fit a whole 32-bit data path, a whole computer in one chip, 32-bit. So it was much more efficient. So at Berkeley, we built some RISC chips, and Stanford built some too. so I'm told. But last February, IEEE had a ceremony, and they installed a plaque at Berkeley recognizing RISC-V as first RISC microprocessor. And so you've been around for a while. When you go to work, and research you did is a brass plaque on the wall. All right, so what happened with CISC versus RISC in the PC era? What Intel did is translated the x86 instructions internally. The hardware, we kind of compiled them into simple RISC instructions. And then any good RISC idea they could do. And so they were very successful in that. And sold 350 million microprocessors a year, which is amazing. And soon the x86 instruction set not only dominated all the desktops, dominated servers as well. Okay, what about the post-PC era, client and cloud? Now, instead of a microprocessor, and this is an important point, is the instruction set. You can get an instruction set as intellectual property from a company like ARM, not just hardware from a company like Intel. And they valued not just performance, but die area and energy. Those were all three equally attractive. And more than 16 billion of these, 2 for every person on the planet last year, and 98% of those were RISC. So that's a different ending than the PC era. So that gets us through kind of the 80s. In the 90s, an interesting idea came along called very long instruction word. And it's about what you think. You would have multiple instructions packed in one long word. And from the hardware perspective, it was really easy because all of these were independent. You didn't have to do anything. You just needed a little bit wider, lots of functional units to be able to specify them. Whose job was hard was the compiler people. The compiler people had to build a compiler that would keep track of all the latencies and make sure there are no dependencies, because the hardware didn't have to do that. That was the job of the compiler. So as an example, they would enroll a loop to get more instructions so that they could schedule. And then if there's the code on the left, and there was a latency between the loads and the adds of 3 clock cycles, so then the compiler would schedule that further, and if there's a latency between the adds and the stores of 4 clock cycles, then you'd put the loads down there. And so you can see there's a bunch of white space, no ops in all of those VLIW fields, and it was the job of the compiler to do tricks like this, to find instructions from other places and stick them in and fill up those slots. Intel, it was time, this address space was running out of bits like Satya talked about this morning, and so it was time for Intel to have a successor to their 32-bit architecture, the x86. They decided to embrace VLIW. They called it EPIC, for explicitly parallel instruction computing. HP joined them in that effort, so HP pledged to use EPIC. Intel was going to use EPIC, and they pretty much told everybody in the world that this is the future of computing. You better join the bandwagon. Now, the first thing that they did, was like the 432. It was late and slow, but they said, well, give us a mulligan. That one doesn't count. We'll do the next one, and it came out and it was better. So what happened? It was an epic failure. So the problem for the VLIW was unpredictable branches were hard to compile for, and then cache misses. Unpredictable cache misses were hard to compile for, and the code size was a lot bigger because of the long instruction words. And so, and this is what Don Knuth said, is basically, it's great. The hardware's easy. You just need this magic compiler, and it was just too hard to write that compiler. So what was happening in the Valley and all across the world is Intel and HP marketing things had this drumbeat that this was the future, and people just gave up on the threat of it. And so when it didn't work out, it became a joke in the industry. And it's called the Itanium, so somebody decided to rename it the Titanic, and like the infamous Titanic ship. And this poster shows software companies abandoning the Titanic. All right, that's the 1990s. The 2000s, instead of instruction set being the big controversial interest, is how should we build, what's the right way for hardware people to build scalable multiprocessors, large-scale machines, to make it easy for software development? And there were two schools. There was what's called a non-uniform memory access time. That is, because they're big and they're distributed, it's going to take longer to get there. So it's versus local, so slower versus faster. The mechanism is called the directory structure. So it can keep everything consistent. It looks like everything's consistent all the time, more or less. And John Hennessy and others at Stanford led projects in that era. The alternative was build what we would call a cluster today. You could connect computers with local area networks and create a service. And there was a project which Jenna worked on. Jenna worked on the Network Workstations project at Berkeley in about the same time. To give you an example of what the NUMA thing was like is John, who was I guess consultant for SGI, they built this origin machine, and here was this cache coherent system that could scale up to 2,000 nodes, and with a scalable network and all of that. And it was designed for scientific computation. An alternative that was done at Sun, which is about as big an SMP as you could build, had 64 nodes, and was designed for commercial processing. But the NUMA was supposed to be, you could see, many times bigger than what you could do with an SMP. The advantages of NUMA are it's going to be, that I thought was easy to program when the communication patterns were complicated. It was just like building it for the SMP, the same programming model, so that should make it easier to port it. Maybe you could, because you could share little tiny items easily with the cache coherency, there'd be less overhead, and you only had to bring over what you needed, not more than that, so maybe you communicate less. So the cluster drawbacks were the cost of administration. If you're going to, a single SMP with 2,000 nodes looks like one system. 2,000 workstations is going to be like administering 2,000 computers. The clusters are connected over the I/O bus, not over the memory bus. That means, and then what people are worried about, and I didn't mention, I got these slides. To find slides on Wednesday, I had to go back to my lecture slides from 2000 to talk about the issues and figure out what they were. But wow, we'd waste a lot of DRAM. There'd be n independent memories. Each would have a copy of the operating system. Each would have a copy of the program. That was wasteful for DRAM, which was expensive at the time. The upside of clusters were air isolation. The separate address space would limit the impact of the air. If in terms of replacement, providing a real-time service, you could more easily disconnect a computer and replace it if it was running. And in fact, the Inktomi folks actually kind of moved the whole machine several miles. They shut down half of it, kept it running, brought it up at the other side. Scale, much easier to go up to large things if you were building out of networks. And then the cost was another big advantage that we argued, that workstations as the building block would be much cheaper to connect together with commodity switches than if you built custom networks with custom boards. So Inktomi, which was spun out of Berkeley, that was doing it was, believe it or not, a very popular search engine at one time, kind of demonstrated that commercially you could do this out of workstations, and then everybody did that. So what happened to all this? I just was looking at this slide, obviously, the other day. So this, you can see on the date, it's 2001. And so at the bottom, I say, ask the question in the class, is the future services built on Google-like clusters delivering gadgets to cell phones? I think the answer to that question was yes. So instead of kind of the cache coherent, hard to build, keep everything consistent way of building big computers of the future, which, kind of an architecture-specific one, the cluster thing won. Okay, so there we are halfway, that's the past. Let's start talking about the future. Moore's law is slowing down. We've had 50 years of Moore's law, but each technology generation is getting a little bit slower than the last one. So the run's over. So maybe single thread performance is improving maybe 10% per year, and you get a few more cores. So maybe you get 30% per year. The price, the amazing Moore's law drop in price, that has slowed down. The latency, which Satya showed this morning, was pretty getting worse. The bandwidth has been getting better, but recently that's been a problem. So people are doing what are called interposer chips. So it's a substrate, and on that substrate, you put a bare processor die and DRAM dies on top of it, but you're limited to how many you can have. So you can get very high bandwidth and maybe even better latency for a small number of DRAM chips. What's happening in solid state, even though Moore's law is slowing down, the flash guys are continuing because they're going to a 3D. They're putting more layers when they build the chips, so the flash technology keeps going. The crossover point here on this slide between solid state disk and magnetic disk is next year. That's the crossover rate, bytes per dollar, next year. So Jim Gray predicted this a little bit less than 10 years ago. Tape is dead, disk is tape, flash is disk. So we're seeing that now. A very exciting announcement was made just a couple of months ago by Intel and Micron. There's been a lot of talk about successor technologies to flash and DRAM. This announcement seems to be a pretty big deal. It's 1,000 times more resilient than flash, 8 to 10 times denser than DRAM, so it should be much cheaper per byte. And then the DRAM access speeds aren't that much slower. I mean, the cross-point access speeds aren't that much slower than DRAM, which is pretty exciting. Now, if this was just some startup company announcing it, I don't know how excited we get, but the fact that it's Intel and Micron making it makes it sure, okay, got to remember to give this talk today. All right. Thanks for reminding me. All right. The storage hierarchy, so what's going to happen from your guys' perspective? The storage hierarchy is getting deeper. I can't believe there's 3 levels of caches on chips today, but there are. Fast DRAM, because it's going to be on these interposer chips to get the bandwidth that they want to get for like GPUs and CPUs together, but it's not going to be very much of it. If the cross-point memory is really going to be there, people think it will, and then solid states with a disk in the background. So better start thinking, that's 6 layers for sure of memory hierarchy, so you might want to think about software it. Okay, how about instruction sets? Where are we on the instruction set side of things? Well, nobody's built a CISC instruction set in more than 30 years. There have been dozens of RISC instruction sets, but we gave up on CISC. VLIW, lots of people tried besides Intel HP that didn't make it. It works for DSPs and the kind of more limited software. So kind of amazingly, RISC ideas are that's agreed to be widespread agreement that RISC ideas are the right way to build instruction sets. So if there's widespread agreement on instruction set principles, why don't we have an open one? You guys get to have an open one. The compiler people have an open one. Why don't we have an open instruction set? And the answer is there's no technical reason not to have one. There's business reasons not to. It's not an error of omission. It's not like Intel and ARM forgot to make it open. Oops, nobody made it open. No, they hired lawyers to go after you if you copy them. Right? And it's not because they do most of the software development. You guys, everybody else does all the software development. They almost do none of it. And you don't need a company that size to design instruction sets. Lots of people could design instruction sets. It's a lot of work, but it can be done. And it's not like the ones they designed are wonderful. They're popular, but they're definitely not wonderful. And it doesn't take a company to verify an instruction set. The things we do in open standards like networking and wireless networking, those are hard standards, yet we know how to make those standards work. Instruction sets are pretty well defined. We can do that. It doesn't even protect you from lawsuits. Right now, NVIDIA is suing anybody who uses Qualcomm. They're suing Qualcomm and Samsung for using GPUs from ARM and from Imagination because they claim it violates their patents. And finally, if it's proprietary, you're tied to the viability of the company who owns it. So when DEC went out of business, they took the Alpha instruction set, which many people like, and the VAX instruction set along with it. They went away overnight. So why are we talking about open instruction sets now? I think the 2 things, like I said, the switch from microprocessors to IP and SoC. So many people could design an instruction set and offer an implementation, even if they don't build chips. And then the ending of Moore's Law, the architects think as a community that transistors aren't getting any better, so we're not going to see improvements in cost, performance, and energy from general purpose things to the first order. A little bit, but not a lot. So to make a big breakthrough, we're going to need domain-specific coprocessors. GPUs would be one version of that. And so we want some minimal open instruction set that you could build upon to add your special purpose sauce. So RISC-V, which we done at Berkeley, where'd that come from? Well, 5 years ago, it was time for us to do a new research project, so which instruction set we're going to design. Obvious choices were ARM and Intel, but they were really complicated, and big lawyers groups wouldn't let us work on them, even though Intel was a sponsor. MIPS, all the opcodes were all filled up, so we couldn't add the secret sauce. So we started a 3-month project to define our own instruction set, and 4 years later we were done. So there's a lot of details. There's other things we did. We taped out a bunch of chips that I'll tell you about. So the funny thing that happened about 2 years ago, we were using it in our classes, and we started getting hate email from companies asking us why we were changing our instruction set we were using in our classes. So we're used to getting complaints, but this was an unusual complaint. And so we checked out what they were doing, and what happened is there was this thirst for an open instruction set, and they found ours and were starting to use it. So for about the last 18 months or so, we've been trying to embrace that. So our modest goal is, world domination. So let me, in the time, tell you a little bit about RISC-V. So it's got this really interesting idea. There's 3 instruction sets, 1 per address size. So we did 32 and 64, that was obvious, and then we did 128-bit as a joke. But then people from the security community kind of liked this idea of a big address space. And then in the data center today, because of flash, we're going to have more than 2 to the 64 bits of flash in a warehouse scale computer soon. You might want to address it. The base is just 50 classic RISC integer instructions. All software runs on that. And now there's optional extensions that you can include in your SoC if you want them, like for integer multiply, divide, atomic operations, single and double floating point, or quad. We have that as well. And compressed instructions for code size. And we reserve opcodes for the secret sauce if you want to add that to your SoC, and a standard 32-bit RISC encoding. So what it looks like is here's you can almost see that from the front row. There's the classic 50 integer RISC instructions for the 32-bit version. And for the privileged instructions, there's just 14 of those. If you want the multiply and divides, there's 8 for those. There's 11 for the atomics. And then there's 34 for the single, double, or quadruple floating point. There's 30 for the compressed instructions. And then it also adds a few more instruction formats for that. That's the full 32-bit instruction set that we've defined. 64-bit, you need to add 12 integer ones for the wider place, and then 4 for the multiplies, 11 for the atomics, and 6 for the floating point. And that is our green card. And I'll be happy to send them to you. I forgot to bring them with me, but it's a popular memento for RISC-V. We've got a full documentation, chip generators, tools, ported Linux, of course, to it. I think one of the exciting things right now is how cheap it is to do hardware, and that's what I'll tell you about. For $250, you can get a board that has a customizable instruction set that runs a full Linux stack with all the compilers you want at 50 megahertz, and you can change it every hour. That's about how long it takes to run the CAD tools. So a minute at this clock, a minute of real time that runs at gigahertz can be done in an hour on the FPGA versus taking a month on the simulator. And you could do a cluster of 32 of these for less than 10K. But besides FPGAs, we've been building chips. So this is 2 technologies. The 45 nanometer top is more than 1.5 gigahertz dual core design. And then this other one is a very power efficient 1 gigahertz design. So we get these things fabbed because DARPA pays for it or donations. What would it cost to go outside and get them? So when I found out the number, we wrote a blog about it. So for 100 small 28 nanometer late technology, what does it cost? So it's $30,000. We surveyed people and they thought it'd be $170,000, which I thought. So $30,000, you can get 100 chips in the latest technology. RISC-V itself is popular beyond Berkeley. India has adopted it as its standard instruction set. So it's kind of amazing. They were one of the people who were complaining about us changing it. So IIT Madras has got $80 million to build six different cores. They wanted to restart they wanted to have their own semiconductor industry, and they want to have their own instruction set. The Low RISC project out of Cambridge has a private benefactor that's going to pay for this, and they're using RISC-V to do an IP-free. One of the founders did Raspberry Pi. They've added capabilities to RISC architecture, RISC-V architecture. They've changed out the privilege spec to do it, and they intend to make about 200,000 of those. And then even research projects besides Berkeley are using it for the research. So the big ideas here, 50 instructions run the whole software stack, optional extensions, reserved opcodes. It's free. Well, people ask what's free. It doesn't cost anything. There's no paperwork. Anyone can use it. Free. And we're going to have a foundation to evolve that over time. If you're interested in learning more, you can go to this RISC site. We're going to have our third workshop will be in January. Academics get to go free. As a result, it will sell out. And I've got time for questions. And if you guys don't ask me questions, I'm going to ask myself questions. So. I'm ready. All right. I've been watching. Nobody's been asking questions. Okay. Oh, there's a question. About changing in floating point formats? Yeah. The IEEE committee meets. To have an IEEE committee, you have to refresh it every few years. The last version of that added 16-bit formats and quad officially. There's another meeting now, but I think those cover things pretty well. We'll certainly be compatible with that. Yes?
Can you say more about the low-risk capability extensions at Cambridge?
Boy, I'm the wrong guy to ask about that. Does anybody, I'm sure somebody here, do you know about no. The question is about the capability-based extensions they're doing at the low-risk project. I don't know the details about it, but they've modified the Berkeley design, put them in, and they contributed them to the repository, so you could find out a lot more about them. It's based on the Cherry work? Thanks. I'm sure that's right. All right, I'm counting, I still got minutes, I know. Yeah.
We've got 1 minute in the back. All right?
Well,
The question I would ask is, so you were showing us that NVRAM is going to win, but on the other hand, that's really pretty far away in latency compared to DRAM. Is there something
that's what I just talked, didn't you pay attention? The cross-point technology is 2 or 3 times lower than DRAM.
Yeah, no, I see. But
That's a very non-volatile, if that's real, that's very exciting.
so what do you see as in terms of latency? Or is that going to be our memory picture?
Well, I thought that was on the slides. There's going to be, in the next 5 years, there will be DRAM on interposers, which will be high bandwidth, but a small amount of it. There would either be bulk DRAM, which will be lower latency, not as high bandwidth, or if this cross-point technology is real, we'll have something that's non-volatile, tremendously cheaper, only factors of 3 slower than DRAM. And the way memory hierarchies work, that'll be pretty interesting things. And then flash, huge amounts of flash. But all that stuff about mechanical latencies, milliseconds, and stuff like that, that's long gone. I think I see Ethan over there.
Yeah, so what I was wondering about is how, if at all, you guys are going to handle vector type instructions.
Great question. Yes, that'll be our next extension. So basically in computer architecture, there's this crazy SIMD stuff that has it's ugly, stupid design. There's this elegant thing that Seymour created, vector architectures, and it can do all of the things that SIMD can do, and you can compile for it, and it doesn't take as many instructions. We're going to have a vector architecture, and that'll be the next extension that we do, over the next few months. That's the one I'm writing that one, so that'll be. We've already got ideas. Okay.
Peter and Sancho both mentioned the marvelous things that come about when you don't have to rewrite your programs for every successive generation of processors.
I don't think I said that. So I mean, binary compatibility is a great thing, right? Intel's made a lot of money for that. But I think in the Internet of Things world, this is less. It's not clear that binary compatibility is an overwhelming issue. You know, if people are writing, you know, we've got all the, any compiler we can compile to our architecture. And then, you know, there's what should we have the Java virtual machine was this bytecode interpreter, which made sense at the time. You know, RISC-V could be a very valid, you know, target going into the future. So I see software compatibility around an open instruction set as a perfectly viable path, you know, commercially viable and interesting path forward. All right, I think my time is. I'll stop myself.
Okay, let's Here's your principal cert, correct size.
Oh, good.